So we stopped here. We started talking about intersecting characteristics, and especially the fact that for non-small, in other words, for large disturbances, the main difference, the main interesting thing is that two forward characteristics, or for that matter two reverse characteristics, can intersect. So either way, if two forward characteristics and two reverse characteristics, if two like characteristics intersect, then you have the possibility of a mathematical discontinuity, okay, which is called a shock. So we will consider shocks in a minute, but remember we are now starting to talk about mathematical discontinuities. Ideal, I should say, mathematical or ideal discontinuities. And an ideal discontinuity, as you know, in any say you're talking about, say this is the x direction, and you're talking about a discontinuity in pressure. So let this be pressure. An ideal discontinuity in pressure would look like this, right? Right here at this point, the pressure is double valued. You don't know whether the pressure is this or this. It's double valued. There's a jump, and that jump has zero thickness, right? It's a infinitely sharp discontinuity. So supersonic motion does allow for mathematically ideal discontinuities in the flow, such as shocks, and these are not the only discontinuities. We will talk about another kind of discontinuity in a minute. Well, in a while, I should say, after we finish talking about a few other things, we will also talk about another kind of discontinuity. But the key thing is that so far we've been talking about mathematically ideal discontinuities. Okay, but surely there are no ideal zero thickness discontinuities in real life. Surely, I mean, this kind of a pressure jump or a density jump, okay, if this is x, for instance, this is not realistic. In real life, there's always a finite thickness. In other words, in real life, this discontinuity surely will look like this. I mean, this is the thickness we're talking about, roughly. If you zoom in here, it really surely it looks like this, right? So if you extend the scale, it might look like a very sharp discontinuity, but if you zoom in, surely the discontinuity is a little more. So what is the thickness? The question is, how wide is the discontinuity? Okay, this is a very important question, okay, very important practical question. Not so important from a formal mathematical point of view, okay, but from a practical point of view, it's a very important question. So what is the thickness? It's certainly, it might well be zero from a mathematical point of view, but from a practical everyday life point of view, when you actually, shocks have actually been observed in the lab and also in near Earth outer space, okay, spacecraft have traversed through shocks. They find sudden jumps, but they find that the jumps do not happen instantaneously, they are a little gradual. So exactly how much is the thickness, and what is the thickness decided by? What physical parameters decide the thickness? Turns out that this is a fairly complicated question, to be fair, but we can understand this from certain basic considerations. We can understand this using stuff that we've done so far. Okay, all right. Now, the main thing to realize is that at the shock, the inertial and viscous forces roughly balance each other, and I urge you to think why. Remember, so far in our entire discussion of shocks, we have been neglecting viscous forces. We have been considering only the Euler equation. We have been neglecting the part of the Navier-Stokes equation that includes the nu, the viscosity. We've been neglecting it. In other words, what this implies is that far away from the shock, okay, viscous forces are not important. So, this is a very high Reynolds number flow, or this is a very high Reynolds number situation. Okay. Now, turns out that near the discontinuity, yeah, viscous forces do start, or viscous effects do start becoming important. They might not be important far away from the shock, but viscous forces, even though the nu itself might be very small, remember in the momentum equation it appears in this combination. This is the combination in which the viscous term appears, right? And what's happening near the shock? Well, the shock is a large jump. Mathematically, it's a large jump. It's a large jump. This is a jump in pressure, density, velocity, everything. In this particular case, let's talk about velocity. So, the jump occurs, there's a large jump here, and that occurs over a very small thickness, a very, very small thickness. In other words, the dV dx is already quite large because the dx is very small, right? Right? So, dV dx is very large, and d square v dx square, which is what this represents, is even larger. So, therefore, even though nu might be small, and as long as there are no large jumps or whatever in the flow, as long as the flow is smooth, this term might not be important, but at the shock, very near the shock, the viscous term starts acquiring importance, okay. And I don't want to say exactly at the shock, but let's so it starts acquiring importance. Let's look at the point where the viscous term exactly balances the inertial term. Okay. Inside the thickness of the shock itself, the viscous term might well overwhelm the inertial term. Okay. And by the time you're done with the discontinuity, it again goes away and the inertial term starts dominating again. But let's now start, I mean, since this is just an order of magnitude kind of illustration, let us now look at the situation where the viscous term just about starts balancing the inertial term. In other words, this. So, this is the viscous term. Right? And this is the inertial term. So, let's look at the situation where they are just about balancing each other, like that, right. Viscous term just about balances the inertial term. Yeah? And of course, the nabla square u is just replaced by d square u dx square, and rho u dot grad, I mean in the momentum equation, this is essentially the one dimensional analog of that. Yeah. So, now let us do the usual thing, roughly speaking. Let us replace du dx by something like u over delta, where this delta is the shock thickness, so to speak. Right? And let us say this. So, by the same token, this u over delta square is very similar to what we used to do earlier. We used to write an L here, remember, but that L was a macroscopic quantity. Here, we are really talking about a very small thickness, and this delta is that thickness. Okay. So, we replace this du dx here by u over delta, capital delta, and we replace this d square u over dx square by u over capital delta square. Okay. And this is the important thing. And once you do that, we immediately find that the delta, the shock thickness, is nothing but nu over u. Okay. It all depends upon the viscosity. In other words, the shock thickness is decided by the viscosity, is decided by the microphysical viscosity. So, what this is saying is that the is decided by the viscosity. That is what this statement is saying. It's a very important statement. It's also decided by the bulk speed, of course. Okay. The faster the speed, the smaller the shock thickness, right? Okay. So, let us go a little farther. Okay. So, that is one thing. The viscosity is a transport coefficient, it's a property of the fluid, but can we now relate this to the microphysics a little bit? Let us see. Now, remember the quantity nu is something like a diffusion coefficient, centimeter square per second. In other words, this is some kind of centimeter times centimeter per second, right. So, this is a velocity and this is a length scale. So, it is some kind of length scale times some kind of velocity, some kind of length scale times some kind of velocity. That is the microphysical origin of the viscosity coefficient nu, right. And the relevant length scale in this particular situation is the particle mean free path, and the relevant velocity is the mean free speed, the mean particle speed. Mind you, we are now delving into the microphysics. This average u no longer represents the bulk fluid flow. This represents the mean speed of the particles that constitute the flow. In other words, we are not looking at the fuzzy picture, the fuzzy fluid picture anymore. We are taking a lens and looking at an element of the fluid and trying to see what the fluid element comprises of. And now, because we are holding a lens, we are able to see the little the movement of the constituents of a fluid parcel, right, say molecules for instance, and we are able to figure out that these molecules are whizzing about at a mean particle speed average u, and the mean free path of these whizzing about is something like lambda. Okay? All right. So, this is important. The other very important thing to realize is this: the sound speed is nothing but the mean particle speed to within a factor of unity. Why is that? Well, what is the RMS speed? Right, some URMS, you remember this, URMS is something like kBt, isn't it, 3/2 or 1/2 depending upon the details. And what is C sub s? C sub s is after all some kind of gamma p over rho, okay. And once you write this as nkt, right. So, this is something like p over rho, which is some kind of n k Boltzmann t over n mp, right. So, the n's cancel out, right, and you have something like kBt here in the C sub s square, sorry. And here too it should be URMS squared. Okay? So, both of these are something like kBt. All right? So, this is one very important realization, which essentially is saying that the mean particle speed is something like the sound speed. Not much of a difference between the two. Okay? And you can verify this, we just showed how it is. If that is the case, and the shock speed u, and now this u is different from this u. This is an average u and this is the bulk speed u. The shock speed is also of the average order of C sub s. Why is that? Because, in other words, the Mach number is okay, it is greater than 1, but not that much larger than 1. And in this spirit where we are neglecting quantities of order of unity, whether it is 2 or 3 or 5, it does not really matter. Okay? We are not talking about Mach numbers of 100, 1000 or things like that. We are talking about mildly supersonic flows. Okay? So, that is why the u is also of the order of c sub s, which means that this quantity, we said that the shock thickness was something like nu over u, right, and we said that the nu is something like lambda average u, which is something like lambda c sub s, and this bottom u is also of the order of c sub s. So, the two c sub s's cancel and we find that the shock thickness is roughly the mean free path. This is a very important result. Okay? So, the shock thickness essentially is approximately the particle mean free path. So, the shock thickness is decided by viscous effects, which is essentially saying this, is decided by viscous effects, and it is around the particle mean free path. Okay. Remember, we are now mixing up the fluid picture and the particle picture. Okay. This is, I mean, although we said very decidedly in the very beginning that when you start talking about fluid mechanics, a fluid parcel is comprised of many particles, say 100 or 1000 or definitely many more. Okay, so that the trajectories of the individual particles and everything are sort of papered or smoothed over. Yeah, and you remove this lens and you cannot see the individual particles whizzing around anymore, and so in that picture, of course, and that is really the fluid picture, and we are now starting to talk about the possibilities of discontinuities in macroscopic fluid quantities such as pressure, density, velocity, and so on and so forth. Okay, but now we are starting to ask the question, well, okay, so these are idealized discontinuities, but surely in real life there is no such thing as an ideal discontinuity. There is no such thing as a zero thickness discontinuity. We are asking the question, what is the thickness of this discontinuity? If we want to answer that question, we have to bring back the lens and we have to start looking at the fluid parcels, yeah, and we have to start mixing up our understanding of particle effects and fluid effects, and that is what we have done here. Specifically, we have to look into the microphysics of the viscosity. Okay, because we said that we figured out that the shock thickness is decided by viscous effects. We already did that in the last slide. And furthermore we ask, well, what is the microphysics of the viscosity? If we look into that, then we find that the shock thickness is roughly lambda, where lambda is the mean free path. So, we are indeed mixing up the fluid and particle pictures a little bit, but we have to do that. If we want to investigate a small scale structure such as the shock thickness. Okay. Now, having said that, we have to also say that there can be additional interesting complications when the gas is collisionless. What you mean by collisionless is, I should elaborate that a little bit. What do you mean by collisionless? This entire discussion presumes that there are many collisions, there are many mean free paths many mean free paths within a fluid parcel. That is what this entire discussion presumes. In other words, what is a mean free path? A mean free path is nothing but lambda. The lambda is really small. There are lots and lots of lambdas within a fluid parcel. That is what the entire fluid assumption is based on. Okay. But this might not always be true. The lambda, the mean free path, might occasionally be quite large in comparison to a macroscopic length scale. In other words, lambda can be, that is what this entire thing refers to, this statement, where there are many mean free paths within a fluid parcel, and in this situation the gas can be legitimately considered as collisional. Okay, and this is the regular picture. This is what happens in everyday situations. Especially in astrophysics, you can run into situations where this assumption is violated. Okay, and the gas is occasionally collisionless. What we mean by that is that the mean free path can be comparable to the macroscopic length scale. Now, I know what you're thinking. You will immediately say that if that's the case, then the fluid assumption simply breaks down. The reason I'm saying all this is because, you know, this entire thing, the shock thickness being decided by the mean free path, if you naively apply that to a collisionless situation, then you'll find that the shock thickness is huge, because the mean free path is large in comparison to a macroscopic length scale. So you would expect that the shock thickness is huge in this kind of a collisionless situation. But when you actually, in some astrophysical situation, you will find that, even in a collisionless situation, the thickness of the shock is actually quite small. It's not comparable to a macroscopic length scale. Okay. Now, the first thing you might, that's the reason I brought up this point, but you might also think, well, if this is the case, if the mean free path is comparable to macroscopic scale length, then the entire fluid assumption breaks down and we should not be talking about fluid dynamics anymore. We should really be investigating the trajectory of individual constituents of the fluid, such as molecules or atoms or as a case might be protons and electrons, and whatever the individual constituents are, and we should not be applying the fluid picture at all. Okay, we should be following the individual particles around. Yes and no. Okay, the problem is, from a practical point of view, from a computational point of view, following individual particles around is very computationally expensive. Right, and you might ask, well, give me a practical example of a collisionless fluid. The solar wind is an astrophysical example of a collisionless fluid. Why do I call it collisionless? The distance between the sun and the earth is 1 astronomical unit. Okay, and within 1 astronomical unit, an average solar wind proton, okay, which is a solar wind, you can consider it to be something like 1,000,000 degrees hot, an average proton. An average proton undergoes 3 collisions between the sun to the earth. Okay. Now, the distance between the sun to the earth is a representative macroscopic scale length, you'll agree with me. Half the distance, or maybe 1/5 the distance, not 1/100th the distance, but say half the distance or 1/5 the distance between the sun to the earth would be a representative, macroscopic scale length. And by the time a given solar wind parcel travels from the sun to the earth, roughly speaking, an average solar wind proton undergoes 3 collisions. Not many collisions, but just 3. And this is a situation where the mean free path is quite comparable, right, to the macroscopic scale length. So this is an example of a collisionless fluid. And guess what? People have been applying fluid equations to the solar wind, disregarding this very important thing, and they have been coming up with pretty good with results that match observations fairly well. So what gives? There's something here. There's some funny thing here which somehow enables the application of fluid equations to a situation, to a collisionless situation where the fluid equations really should not be applicable. So what gives? The thing is, I really should be writing lambda, not really lambda, but lambda c, where lambda c refers to particle-particle collisions. Okay, so this lambda c, which is the mean free path governing particle-particle collisions, right, might well be comparable to the macroscopic scale length, but there can be other collisions. Okay, in other words, the solar wind is turbulent, and there are other kinds of scattering centers. Okay, and the protons might well be colliding with each other in a particle-particle way very infrequently. Okay, but they might be colliding much more frequently with these other scattering centers, with these turbulent scattering centers. Okay, so the collisions of protons with turbulent scattering centers are much more frequent than the collisions with protons with each other. Okay, so in other words, these turbulent scattering centers lend, the fact that the turbulent scattering centers are present lends a fluid-like character to the otherwise collisionless solar wind. So this is the thing. So therefore, when you're talking about shock thickness and things like that, you will be talking about lambda, all right, but no, you should not be considering the particle-particle mean free path, which is huge. You really should be considering an effective mean free path which gives you the average distance for collision between a solar wind proton and a turbulent scattering center, a magnetic irregularity, for instance. So that turns out to be much smaller than lambda c, which is of the order of a macroscopically large distance, and therefore the shock thickness is really decided. So essentially, you're talking about a situation where the viscosity is not due to particle-particle collisions, but due to particle something else collisions, and that something else can be a magnetic scattering center, and that is what decides shock thickness. So this is, of course, an advanced topic, which is why I said there can be additional interesting complications when the gas is collisionless. So with that, we will stop here, and we will return to a discussion of idealized discontinuities when we meet next. Thank you.